Hey class, this is Mr. Hofstad here with lesson 7. It's just a short one, no examples, but I'll just walk through the notes with you because they are a little interesting. Got some cool stuff going on here. So we're looking at atomic spectra and breaking it into 3 different categories. There's different applications to this. I'm sure some of you have seen what we've got going on with these bands, right? Different spectrum of colors with dark bands or a continuous Roy G. Biv spectrum. If any of you have played Spider-Man on PS4, there's some fun little puzzles involving these spectrum because Spider-Man is a nice physics nerd that we can all aspire to. So our first type of emission spectra is a continuous spectra. So this is the kind of electromagnetic radiation that results from heating up an object, right? This is how our old-fashioned incandescent bulbs that we should all have thrown out by now and switched over to LED. But the original light bulbs just worked by heating up this filament in the middle here, and that would release a continuous spectrum of electromagnetic radiation, where all the frequencies of that EMR are present, all the way from red to violet. So this was a result of heating solids, liquids, or dense gases, and it produces a continuous spectrum. So classic example is just the filament in a light bulb. Another one would be a piece of iron or your stove even. As it begins to heat up, it'll start to glow red. If you keep it going hotter, you can't really do it with your stove, but if you ever watch Forged in Fire or some YouTube videos on getting metal super hot, it'll go from red to orange to yellow, and eventually you can get even a piece of iron to burn white hot. And that's an example of this continuous spectrum. So that's actually a result of our atoms colliding with each other. So as it heats up, we're adding kinetic energy, right? So heating means we're raising our, okay, that's not going to work. We're raising our kinetic energy by heating it, which means our atoms are moving around faster, more collisions, right? And an important part about that is inside the atom or surrounding it, we have the electrons. And as we have the atom moving around, the electrons are kind of following them around, more and more different random motions and different oscillations, right? The electrons will constantly be circling around the nucleus, and as the nucleus of the atom collides with other atoms, right, these electrons will kind of bounce around a bit. They'll start oscillating and vibrating in and out at different frequencies, right? And once it's hot enough, all of those frequencies from red to violet will be emitted by that hot object, thus a continuous spectrum, right? So as long as it's hot enough, the atoms are moving around, bouncing off each other at such a rate that the electrons are oscillating at all of the frequencies of the visual spectrum, and those oscillations are then producing the electromagnetic radiation at all frequency, at least all the frequencies in our visible spectrum. All right, so that's our first one, continuous. We have every single frequency of electromagnetic radiation being emitted. Our next one, right, so this would appear just like white light until we use our prism to separate it into its component wavelengths or frequencies, and we'll get our nice Roy G. Biv rainbow as a result. All right, if we tried to do this with our low pressure gas exposed to a high voltage, so classic example would be a neon sign, right? We just have gas kind of collected inside a tube, pressure is lowered, and we're going to run a current through it. And when we're running that current through it, we are exciting those atoms, right? So as this voltage is running across all of those gas atoms, they're actually going to kind of interact with that electricity and those additional electrons, and they're going to start vibrating and oscillating at very distinct, discrete bands. So every type of gas will have a different emission spectra that will result from running a current through that gas. So let's say we got hydrogen gas here, right? It's going to appear to be a certain color. I'm pretty sure hydrogen would appear yellow. I'm not 100% sure though. Maybe not. We've got no yellow there. Anyways, this would be all of the discrete frequencies emitted, the electromagnetic radiation emitted by this hydrogen gas. So we have a red band, a green band, a blue band, and a violet band. So that's the specific emission spectrum or special signature of hydrogen. So you can actually determine the composition of stars or of any gas you have that you're running a current through using these distinct bands. So this all has to do with our atoms and their electron states that those electrons will prefer to or only exist at, which will come up more in lesson 8 to 9. So this idea of these discrete bands and these very specific frequencies being let off by these gases with voltage running through them couldn't be explained by classical theory, right? That idea of the wave theory of EMR couldn't explain why most of these frequencies are missing. So classical theory here, not just wave theory anymore, we're also thinking about the different atomic models. So we needed to move into this Bohr model to get a better understanding of why different elements, different atoms would have different emission spectrums. All right, and these two, emission spectrum and absorption spectrum, are very closely linked. When we have this hot object emitting its continuous spectra and that white light passes through our unexcited gas, so in this case we have hydrogen in a tube, we're not running a voltage through it. This is just regular old unexcited non-charged hydrogen gas, and as the white light passes through it, these hydrogen atoms will actually absorb the same bands that an excited version of hydrogen would emit. So something's going on here. The bands are the same frequency of the electromagnetic radiation that hydrogen would emit. So the same frequencies, the same wavelengths that our excited gas emits correspond to the unexcited gases absorbing those wavelengths. So this all has to do with electron states and where they orbit around and the energy levels associated, which is going to come up next lesson. If you feel like working ahead on that before my video comes out, I'm not even sure if I'll do a video. Mr. Holloway has some posted, and you can find that on his YouTube channel, which is linked. So feel free to kind of play with these ideas in your head. Go over these homework questions. It's not super long. And just kind of start mulling over this idea that electromagnetic radiation can be emitted in different ways, right? Different types of spectra, either continuous or an emission or an absorption. And it's all related to what type of atoms we are working with and whether they are absorbing the energy or the photons that passes through them, or whether they're actually emitting the photons by being excited. All right, all we got is 1 page of homework today, just working through these classifications of atomic spectrum and then doing some nice matching, very similar to Spider-Man. All right, I will be in touch with you all. Good luck, stay safe, and have some fun with physics. Take care, guys. See ya.